Hello everyone, and welcome back to Mitchell's Physics Review. Today, we're going to be working on oscillations. Let's take a look at our problem. A 0.26 kilogram block resting on a frictionless horizontal surface is attached to a spring whose force constant is 83.8 newtons per meter, as in the figure below. A horizontal force, F, causes the spring to stretch a distance of 5.14 centimeters from its equilibrium position. First, before we get into the problems, let's take a look at our givens. We were given that K, or the spring constant, is equal to 83.8 newtons per meters. We were given the mass is equal to 0.26 kilograms, and we were given the position is 5.14 centimeters, or 0.0514 meters. Now, let's take a look at part A. Find the magnitude of F, or find the magnitude of the force from the spring on the block. To do this, we know the force of a spring is equal to the negative of the spring constant times the stretch, which is x in this case. So both of these values were given to us, so we can multiply them together, and we get 4.31 newtons. The reason why we don't include the negative in our answer is because it only asked for the magnitude, not the direction as well. Next, let's take a look at part B. What is the total energy stored in the system when the spring is stretched? What's important to know before we look at the mathematical side is that when the spring is completely stretched, all the energy should be stored elastically. So then we can start by writing an equation that the energy total is all equal to the energy stored elastically. Then we can plug in our equation for elastic energy, which is 1/2 kx squared. From there, we plug in the given values, k and x, plug into our calculator, and get that the total energy is 0.11 joules. Now, let's take a look at part C. Find the magnitude of the acceleration of the block immediately after the applied force is removed. For this step, we're going to use one of the fundamental equations in physics. Net force is equal to mass times acceleration. From our little free body force diagram over here, we can tell that Fn and Fg will cancel out and will not cause any motion. The only force that's causing a motion is the elastic force. So, once we rewrite our equation to solve for acceleration, which is acceleration equals net force over m, we know that the only force causing a motion is the elastic force, which we solved for in part A of 4.31 newtons. So we can plug in 4.31 newtons for net force, and we can divide by the mass given of 0.26 kilograms to get an acceleration of 16.57 meters per second squared. Now let's take a look at part D. Find the speed of the block when it first reaches the equilibrium position. For this, we know that all the energy is going to be going from kinetic to elastic. So we can set elastic energy equal to kinetic energy. For elastic energy, we can plug in 0.11 joules, which is what we solved for in part B. For kinetic, we can plug in the equation 1/2 mv squared. From there, we can rewrite the equation to solve for v and plug in the given mass. Finally, we put it into our calculator and get that v is equal to 0.92 meters per second. Next, let's take a look at part E and F together. If the surface is not frictionless, but the block still reaches the equilibrium position, would your answer to part D be larger or smaller? What other information would you need to know to find the actual part in this case? Well, let's start with part E. We know that our answer to part D, or the speed, would be smaller because friction would be pointing in the opposite direction of the motion in this case. And friction would also cause the object to lose energy due to heat. So, what does that mean? Well, whenever we talk about a loss of energy within a system, we talk about an object slowing down. Versus whenever we talk about a gain in energy, we talk about an object speeding up. So if the object is slowing down, plus it has friction pointing in the opposite direction, we know that the speed will be smaller than if it was a frictionless surface. For part F, what we would need to know to calculate the actual speed of part D would be the coefficient of friction. That way, we could determine how much is actually lost due to the collision between the floor and the block. Now, let's take a look at part G. What is the largest value of the coefficient of friction that would allow the block to reach the equilibrium position? The key word being here, equilibrium. So, in part G, we know that at equilibrium, all the energy is stored elastically. So, we can set elastic energy equal to the working energy due to friction. Next, we can replace elastic energy and working with their equations. For elastic energy, we can use the equation 1/2 kx squared, and for working, we can use the force times displacement. In this case, the frictional force is kinetic friction times the displacement of x. From there, we can cancel out an x from both sides. But now, we're left with 1/2 kx equals fk. We need to find a way to substitute in the coefficient of friction because that's what we're trying to solve for. It will be easiest to do this if we set up a free body force diagram. So, since our object is in equilibrium, we know that all the forces should be balanced. So Fn and Fg should be balanced, and Fk and Fel should be balanced. It will be particularly helpful if we set up our equation in the y direction, which would be Fg is equal to Fn. Next, we can use our equation for kinetic friction, which is Fk is equal to the normal force times the coefficient of kinetic friction. Then, for the normal force, we can substitute in Fg and make it Fg times the coefficient of kinetic friction is equal to the frictional force. From there, to get to our final step, we can finally substitute in mg for Fg to get it to read that the kinetic frictional force is equal to mg times mu k. We can then substitute that in for our frictional force in our equation. Then we can isolate mu k, or the coefficient of kinetic friction, and it reads mu k is equal to kx over 2mg. Finally, we can plug in all of our given values, which is k, x, and m, and then we know that g is 9.8. From there, we can plug it into our calculator and get that the largest coefficient of kinetic friction is 0.845. So, what did we learn? I learned a lot today, but what did I need to improve upon? I needed to improve upon drawing the picture. At first, I kept getting confused about part G because I wasn't drawing the picture and I didn't understand equilibrium should mean balanced forces, which led me to not having the right equation when I tried to plug Fg in for Fn when we were looking at our kinetic frictional force. So, that's what I learned, is to always draw a picture when you're stuck. It never hurts, it only helps you to visualize what is actually happening and the physics of the situation. I hope you learned a lot today, just as I did, and I hope you remember to draw your pictures in your future. Mr. Lusher will thank you. Have a great day, everyone.